So our operating system of the day is called OpenVMS, and this was released in 1977. It was originally released by Digital, also known as DEC to all those old fogies. And DEC was actually acquired by HP, so I guess you could say this is one of HP's many different operating systems. They have other stuff. Now, is that their logo now? No, that's their old logo, which is actually awesome, you know, like a shark or something. When HP acquired it, they got rid of the logo, so I'm going to show you the cool logo. Alright, now this operating system should also be known as the operating system that has had way too many different names. It started out being called Star, then Starlet, and then they were looking at things like VAX11 VMS, VAX VMS. Why all these different names? I don't know. They all sound pretty bad. But in the end of the day, the VMS stands for Virtual Memory System, because obviously that was going to be one of the focal points in the implementation of this particular OS. Now this operating system has been around, and it has all of the things you'd expect. It has time sharing. It even supports batch processing, which is pretty cool. It does transaction processing. What that means is that it actually has a built-in database right into this operating system. And it was never really meant to be a user's operating system, although they did do a brief foray into OpenVMS for the desktop, and they offered a GUI, and yeah, that did take off. So this is really meant to run on servers, and it supports all kinds of different things that are related to server-based operating systems. So it's got TCP/IP built in, which at the time was a big deal. It also supports DECnet, which was Digital's own protocols for transport and network layers, which we don't cover in this course. Then of course you've got distributed file systems with versioning. That's really cool. It had things like great security, but one of the most notable things about OpenVMS is its stability. So it is capable of running for very, very long periods of time without experiencing a kernel panic, or the operating system telling you, hey, you need to reboot because I did something and I don't know how to handle this, or any of the above. And in fact, there have been OpenVMS installations out in the wild which have not shut down or been restarted in over 10 years. I cannot think of an operating system that is that stable. When I think about my Mac, I think, oh, well, you know, every month or so it tells me to update it, and then their updates crashes all my programs I have. And then if I'm thinking about Linux, I used to play games. So I started using Linux in '97. And it was always a game. How many kernel panics can I get? And it was a challenge because I wanted to get as many different ones as I could. My favorite, by the way, is LP0 is on fire. LP0 being the printer port. I love that one. But yeah, Linux is not stable. It has kernel panics all the time. There are updates all the time. Windows updates itself every 3 days and turns into some kind of unusable state until you do the update. In which case, after you've done the update, then it changes all your settings and reboots. It's, yeah, this is actually stable. So that's actually really cool. Now this is actually still under active development. So this is not an operating system that has fallen by the wayside and we've given up on. People are still developing OpenVMS. It is still being used, and you actually see it with the Itanium line from Intel is where it tends to be used. So that's kind of fun. All right, so before we get back to virtual memory here, some things to keep in mind is that you have a midterm next week. I know, you're not excited. You're all terrified, I'm guessing. Just some reminders again, and I know I keep reminding you of this, but I want to make sure you are very aware of the resources you have available to you. If you go onto the course website under, I think it's exam information, there are sample problems. Those sample problems are actually all of our previous midterms and solutions. And if somebody sends me a reminder on Piazza, I will post the ones that are missing, and I'll post those to Piazza. I don't have all of them, but I have the more recent ones. So you have lots and lots and lots of previous content to study from. What does your midterm look like? Every other bloody midterm. Because you know why? We take the LaTeX of the previous term's midterm and we just change the questions because we're too lazy to write a new LaTeX file. But yes, it is all done. Now, if that is not enough for your studying purposes, there are also review problems that have been provided from students over the last 20 years or so, and you're welcome to take a look at those. But do be careful because they talk about things that we don't. And if you see the word nachos, yeah, maybe run the other way. Oh, excuse me. All right. So that's the material you have for the midterm. On Tuesday's class of next week, we will have an in-class review session. It will be mostly problems that are being provided to you to try, and then we'll go over the solutions. If there's any particular type of problem you would like to see, please do let me know, and I will try to, if it isn't already in the slide deck, I will try to add one to it. And then on Thursday of next week, so the day after your midterm is Halloween, we will actually, of course, be doing assignment A to B in class. So that might be something you might want to actually come. Well, I guess you don't have to come because it's a video, right? All right, so then back to talking about paging. Oh, yes, one last thing. You probably want to know what's covered on the midterm, right? It's everything up to and including paging. So that's single level and multi-level paging, but nothing beyond that. So, yeah?
The operating systems of the day, those aren't tested.
No, that's not tested. This is not a history class, so I'm obviously not testing you on it. Although, fun story, we actually used to in CS, and I don't know if they run it anymore, but it used to be every 2 years there was a history of computing. And I know there was an equivalent in math as well that was run every 2 years or so, but I haven't heard about it in a long time. I always wanted to take it though. All right, so let's go back to virtual memory. So we talked last class about single level paging. And of course the problem with single level paging, well, let's not talk about the problem. Let's first just talk about what it is. With single level paging, what we wanted to do was we wanted to solve that fragmentation problem that segmentation has and dynamic relocation has. And we noted that the fragmentation actually arises from the fact that each of our allocations of physical memory were a different size. And unless we actually want to have some kind of memory defragmentation algorithm going on, which we don't because it's slow, then we need to make sure that all of our allocations are actually the same size. And that's how paging actually works. So we're going to logically, that's with code, divide physical memory into two equal size chunks we call frames or physical pages. And we're going to subdivide virtual memory into equal size chunks called pages. And pages and frames are going to be the same size. And now the idea is we can take, if our address space has, say, 7 pages for the code segment, we can take any one of those 7 pages and map it to any frame we want. Any frame. They do not have to be contiguous in physical memory. You just find any frame that works and take it. Now, of course, that's going to complicate the actual address translation, and we then needed to use a page table to keep track of, for each individual page, exactly which frame does it map to. Now, the interesting thing about these page tables, at least for single level paging, is that our page table must have an entry for every single possible page. And the reason for that is because if you look at an address space layout, you don't have the code and the data and the heap and the stack all tight together. there's space between them. So you'd have some elements of the page, some pages used here, some used over here, a bunch not used, and then some used over here. And to account for that, we have to have an entry for every possible page. And then we're going to mark whether the page is in use with the valid bit. Now, the problem with this, of course, is that if you look at the size of this page table, each of those page table entries take a certain amount of space. And it's entirely possible that your page table ends up being significantly bigger than the address space actually needed by the program. So if we're going to use virtual addresses that are 48 bits in size, which is very common today, then in our page table entries, if they were only 4 bytes in size, then my page table for this particular setup is 256 gigabytes, but my address space for Hello World only needs 1 kilobyte. That's ridiculous. I don't even have that much RAM to store the page table. And the page table being stored in the kernel, it's like, what are you going to do? Are you telling me that the page table takes 1/4 of my 1 terabyte hard drive? That doesn't make any sense. So single level paging, it can work, but it doesn't really scale well. So to help it scale, we kind of do the same thing we do to organize our files on our hard drive. We are going to create a tree, a multi-level page table. And the idea is we don't create a subtable if there are no valid entries in it. And then everything with the exception of the leaves of this particular multi-level page table contains not page-to-frame mappings, but page-to-table mappings. So all of our upper layers, our directory, which is the root of this whole system, when you look up a page number, it doesn't give you the frame number. It gives you the address of the next level page table you need to look at. And then you'll map the next page number to the next table, and so on until you get to a leaf, in which case the page number finally does map to an actual frame number. All right. Now, this has the potential in practice to actually mean that our page tables are much, much smaller and contain fewer invalid entries than its single level counterpart. So before we had 16 entries in our single level table, and of those 16 entries, 9 of them are invalid. So over half of the entries were actually useless. And if we turn that into a 2-level table, instead of 16 entries and over 50% of them are invalid, we now have fewer entries, only 12, and of those 12, 3 are invalid, so only 25%. That's really awesome. Now, does that mean that multi-level paging is always going to produce a smaller page table than single-level paging? No, it's not. Because if I were to use every single page of virtual memory, my table for multi-level would be a lot bigger. Because in addition to all of the leaves needing every single leaf table, I would need all of the structure above it. So there are instances where a multi-level table would be bigger than the single-level counterpart. But in practice, that's not something you're going to encounter. We use multi-level paging in operating systems today. And in fact, Windows and Linux tend to use 4 levels for their paging. Now, we ended, I'll come back to address translation in a minute. We ended talking about how many levels you should have. And that's actually a really good question. Well, as it turns out, if you look at how modern operating systems actually do virtual memory, they do this thing called on-command paging, which I've mentioned before. And the idea is you only load the pages of the address space into RAM when you actually need them. And that means you always have a fair amount of available RAM, or you can actually run many, many more processes than you technically have memory to support. Or it also lets you run a program that requires more memory for its address space than you actually have in your system. So on-demand paging is a really important thing. Well, all of those pages of the address space that are not in RAM right now, where are they living? They're living on your disk. Disk operations are slow. Not just slow, they are really, really, really slow. Orders of magnitude slower. And we want to make sure that when I need to load a page, part of my page table from the disk, I want to have as few reads and writes as possible. So in order to ensure that actually happens, it is good practice to ensure that each sub-page table fits on exactly one page of memory. Because each of those, that is usually the size of a read or write on your disk, which means that when I want to read or write a table from a disk, I only have to do one read or write instead of many. So it's very, very convenient to have that rule. With that rule in mind, we can then figure out exactly how many levels we need in order to obey that convention. Now, there's the method that's kind of shown on this slide. So you compute how many total pages of virtual memory there are, and then you're going to compute, well, how many page table entries can I fit on a single page? Which will tell you roughly, well, if it tells you how many entries you can fit on that page. And then after you've done that, you keep dividing how many pages are left until you figure out how many levels there are. Now, there are easier ways to do that, and I'll show you that in a minute. So going back just to remind you of how address translation works, what you're going to do now is our MMU has not really changed. We still have a single register that is the page table base register. That page table base register is pointing to the root of the tree. And what you're going to do then is our address now has multiple parts. The lower level, or the lower part of the virtual address is the same. It is still the offset. It is still only related to the actual page size. So the lower part did not change. But the upper part did change. Instead of being a single page number, it is now made of a bunch of page numbers. And what you're going to do is you peel off the first page number, you index the first table. If it's valid, it gives you the address of the next level table, and then you grab the next page number and the next table, and you just keep going down the chain. And if at any point the page table entry says invalid, you throw an exception. Once you've gotten to the end of this little path, that is the leaf of the tree, then you will have the actual frame number, and at which point the address translation is exactly the same as it is for single level paging. You take the frame number, you multiply it by the page size, and you add the page offset, and you're done. Now, nobody actually wants to do that math, so of course the other way that you can do it is you can actually separate it out into bits and actually say, oh, this is my frame number, it goes in the upper bit, so I'll just put it here, and then just take the offset and drop it down and turn it back into hex, and you're done. All right. Now, there's a bunch of formulas that are really important for this, and I'm going to switch over to the board now. I want to make sure I get every single one of these formulas up here. And don't worry, I have a virtual memory guide that also has all of these formulas and examples of how to use them, and I will be sure to post that to Piazza. But let's just do this for now. So the first thing I need to do in order to do a paging translation is I'd like to know, well, how many bits do I need for the page offset? The number of bits I need for the page offset is only related to the page size. All right, that's easy. Now, in order to do multi-level paging, one of the things that I need to do is I need to actually figure out how many levels there are so I can figure out how many bits I need for each of those page numbers. So we're going to start by figuring out how many page table entries can I fit onto a page. So, number of PTEs, that's page table entries, per page, is the page size divided by the size of the page table entry. And the size of the page table entry will always be provided to you. We're never going to ask you to calculate that. So, for example, if my page size is, let's say, 2 to the 12, that's 4 kilobytes. And if my page table entry size is 8 bytes, just for the sake of discussion. So I will divide that by 2 to the 3, which means I can fit 2 to the 9 PTTs per day. All right. Now that I know how many entries I can fit onto a page, the next thing that would be useful is to figure out, well, if I can fit 2 to the power of 9 entries on a page, how many bits do I need to index that table? So the bits for the page number is the log of the number of page table entries per page. So in this particular example here, where we have 2 to the power of 9 page table entries per page, we need 9 bits to index that table. Not too bad. All right. How do we calculate the number of levels then? Well, we can do it now. So, when we are giving you a virtual memory system, we will tell you how many bits we are using to index virtual memory. We'll say that is V bits. So V bits is used to index our virtual address. We take V bits and we subtract the bits for the page offset. Which leaves us with some leftover amount that we can use for our page numbers. So the next thing that we're going to do is we say, okay, we've got whatever bits are left after taking the offset. We divide that by the number of bits we need for page number. And since we can't use a fraction of a bit for a page number, we're actually going to take the ceiling of this. And that tells me how many levels I need. And that's it. Now, you might be wondering, well, what if it doesn't work out evenly? What do I do then? It's okay. Because so long as the table is smaller than the page, you're fine. If you want to picture it, really what this map is doing is if you take our multi-part address, so here's my multi-part address, I'm taking these bits, those are the offset bits, and then I'm just going to take, if X is the number of bits I need for the page number, I just take X, 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 and then I have Y bits left over here, where Y is less than or equal to X. We're done, we're fine. Now, you will see in some of the examples that are posted to the course website and some of the solutions that we have that where we put and how we distribute those page numbers or those page bits, some people, like myself, I will always put the fewest bits in the root position, the directory position. Some people will spread them out so they're all the tables are a little bit smaller. We don't have a convention for how you should do it, so we're not going to ask you a question unless we specifically state which convention we want you to use. We try to be fair, right? All right, any questions about these formulas? Okay. All right then, what I've got for you, if I can dig it out of this bag. All right. So we have a multi-level paging problem, right? To see if you understood the math and everything we've done so far. So take the next maybe 8 to 10 minutes and see if you can do it. I'll let you guys pass these back. This is posted online as well, so don't worry.
basically, yeah. That's just I mean, maybe not converted to rows and
Remember when you're doing these that try not to use a calculator because you're not going to get one on the exam.
Because I know there's no access to memory. Like, it is.
more over
Yeah, well, I mean,
okay,
yeah.
bits is page number, there's the log, the number, I was just here. 60.3 is 48.
Yes.
Yeah. Don't bother. You don't lose any money, guys. It's not taken away. You weren't using any offset bits when you're doing paging, right? You're just using page the format is like that, right? Offset is next to it. Page offset is next to page.
Yes.
Because the number of bits to address, the version of the address. It might not be the same one.
That's all you need. That's right. So, I'm only good now. Questions. I have more. We have 44 bits there for accessing those, so. Yeah.
Alright. So the first few parts of this problem should be simple application of the formulas, which I had on the board. And then I'm going to guess to say that the majority of you spent your time on the last part and puzzling over that one. So let's do the first three parts real quick then. So it says how many bits of each virtual address are needed to represent the page offset? 20. Why is it 20? Well, because the page size is 1 megabyte or 2 to the power of 20 bytes. You take the log of the page size, that's how many bits you need to index. So, question 1 is 20 bits. Then it asks, what's the maximum number of entries in an individual page table?
So we want to take the log of the page size where the page size is in bytes and not bits.
That's right. Yeah.
But
We
that's-
do byte-based addressing.
Okay.
So each bit is a single bit can address 2 different bytes. Okay. All right. So what's the maximum number of entries in this page table? Here's somebody saying 2 to the 16. That is correct. It's 2 to the 16. Why is it 2 to the 16? Well, the size of the page is 2 to the power of 20. The size of the page table entry is 2 to the power of 4. You do the division, you get 2 to the 16. It's just applying the formula. These are formulas that you should memorize, but hopefully when you're looking at them, you can see exactly how they work. The third part is how many levels do we need? Anybody? 3. All right. Anyone disagree with these answers up here? Any questions about these 3 parts? Yeah.
So just to confirm, we never have to convert the bytes to bits.
No. We don't need to do that.
Right.
We do byte-based addressing.
So why does the question ask how many bits of virtual address?
Because that's how many bits we use for the address. All right, so then the next question is a fun one. Okay, it's fun for me, probably not fun for you. We have an address space. That address space uses a contiguous 128 megabytes of virtual memory starting at address 0 and going to 2 to the power of 27 minus 1. And we want to know how many tables exist at each level, and in each of those tables, how many valid entries there are. So, first part is how many page tables exist in each of the 3 levels. Does anyone have an answer to that they are willing to share?
Is there 1 in the first level?
Yes, because there's only 1 group. Good job, you got 1 mark. How many at the second level though?
2 to the 16.
Nope. Yep,
1.
it is 1. And what about the third level? Guess Pardon? I heard someone say 2 to the 7, and what was your guess? I'm guessing also 1. It's also 1, actually. So for question 4, there is 1, 1, and 1. And the number of valid entries in this one at the root is just 1. And the number of valid entries in this table is just 1. And the number of valid entries in the last one is finally 2 to the 7. Now, you may be wondering and totally confused as to how I arrived at this answer. And because this is operating system, so we don't require you to do any kind of proof, I'm going to show you how to do this with a picture. That's valid justification in this course, by the way. It's not CS351, where you need to do induction in 3 pages of stuff. All right, so here is my virtual address. My virtual address is 64 bits. Of these 64 bits, 20 are for Yawson. And then I'm going to do 16, 16, and I don't remember how many's left over. 12. I can't add it sometimes. That's my phone. I don't know who, in the last week, it's a spammer, by the way. I don't give out my phone number. It's a spoof of the Justice Department trying to say they're going to arrest me. It's garbage. Yeah.
If you do get arrested, what's the other extension on?
I don't know about that. All right. Let's settle that. So let's look at the virtual address here. It has 4 parts. The lower 20 bits are for the offset. The upper, however many that adds up to, are the 3 page numbers, which I have set aside 16, 16, and put the fewest number of bits in the directory so we have it. Yeah, I like 3 levels. Now, for this address space, it uses a contiguous block of 128 megabytes starting at address 0 and going to address 2 to the power of 27 minus 1, which means that every valid address in this address space uses only the lower 27 bits. And all of the higher bits for each valid address are all 0. So, 20 and 7. Now, how do we do? What I notice here is that, well, number 1, we only ever have one root. Trees don't have multiple roots. It's not that kind of world. So, there's only ever one. Now, I know that for every valid address in this address space, the upper 12 bits are all zeros. Since all the valid addresses only have zeros in the upper 12 bits, that means that's the only valid page number in the root, which means there's only one valid entry there. If there's only one valid entry in the root, then there's only one table in the middle. Because you can only have a table if you have a valid entry. So we have only one here. And I know that because I'm only using the lower 27 bits of the address, that all 16 of these bits are also all zeros. Which means that there can only, since there are valid addresses, only one valid address or only one valid entry could possibly exist in this table here. Because these are all zeros for every valid address. Which means, since there's only one possible valid entry in this page table, there's also only one page table at the bottom. How many valid entries are there in this one? How did I get 2 to the 7? Well, of these 16 bits, I'll use 7 of them. The lower 7 bits are non-zero for some of these addresses, which means, since each bit can index 2 things, that's 2 to the power of 7 valid entries. I love this problem. So, a challenge for you. Let's change it up every time I choose a different number. Trying to do the same problem. Let's have you try it for 58 bits this time. Not right now. Think about it. You can share your answer on Piazza and I'll let you know if you're right or wrong. I'll have to think about it because I don't have it memorized, because I always choose a different number every turn. All right. Yep.
Sorry, can you explain again how you know that there's only one valid entry in the second level?
So I know there's only one valid entry in the second level because I know that for every valid address, these 16 bits are all zeros. Okay. Which means that there's never a case where they're not all zeros. I still know there are valid addresses below me, but I know that I'm not actually using, and none of the bits are going to be 1 in this area, which means that every single valid address would be having that second level page number as all zeros. And since they all have that same page number, that means 1 entry. All right. So I'm going to move on then. If you have more questions about this, by all means ask them outside, come to office hours, so on and so forth. All right, so let's bring this back. Just a brief review of what is going on in both the MMU and in the kernel of the operating system. So what we find is that the MMU does the actual address translations itself. That is really the MMU's only job, is to translate the physical addresses, and when it can't, it raises exceptions. It does nothing else. Nothing else. It's a piece of hardware. When the exception is raised, the kernel is responsible for figuring out what that exception is and handling it. So, for example, if it's an invalid address, the kernel will detect that the exception was raised due to being invalid, and the kernel will panic appropriately, or kill your program. Well, in OS 161, it just panics and dies, but you'll fix that later. All right. What else does the operating system do, though? The operating system is responsible for implementing virtual memory and managing it. So that is, it's responsible for creating the page tables. It's responsible for mapping the pages to frames. It's responsible for destroying those page tables when the process's address space is destroyed. It's also responsible for, on a context switch, updating the MMU to tell it the address of the new process's page table. So all of that management is actually done by the kernel itself. So there's lots and lots of things done. Now, we have a bit of a problem. So here's the problem. I'm going to draw a bit of code on the board here. That'll make this more fun. Good. So let's draw an assembly program. Add boring program. I don't know what it does. It's a bunch of assembly. Okay. So, as you know, for programs, they are all using virtual addresses, which means the program counter is technically speaking a virtual address which needs to be translated by the MMU. So this is what's going to happen. So I'm at instruction 1, I am the MMU. I get an address for the program counter add, and I say, oh, okay, I'm going to go to RAM, I'm going to grab the page table entry, and I'm going to bring it back to me. Oh. That just gave me the index of another table. Oh, I better go back to RAM again. And I bring it back again. Oh, I got another level. Oh. Okay. I don't want to do that much walking. So, let's pretend we're going to do single level tables for now. That'll be less walking. All right. So, I do the translation, grab the page table entry from RAM for add. Then I move on, and then I execute the add instruction, and I move on to the next instruction, which is sub. I would point out that the probability that add and sub are actually on the same page of virtual memory is really, really high. Because they're sequential instructions. Which means that on the very next instruction, guess what I get to do to translate a program counter? I get to go back to RAM again, grab the page table entry, and bring it back. And then on the next one, which is another add, I go back. I'm going to walk back and forth. And the problem here isn't so much that I keep going to RAM. The problem is that because probabilistically speaking, each of these instructions technically would likely live on the same page, I just grab the same page table entry like 6 times in a row. That's a waste of time. And it's not just when we're looking at sequential instructions that this actually happens. This actually happens if we were trying to, say, read or write data in an array. Arrays, we see it in most languages, are actually stored consecutively in memory, that is in a contiguous block. If I have a loop that is doing something to each element of that array, then I'm going to keep grabbing the page table entry, probably the same one, for each of those elements of the array. At worst, it will be, most arrays are, 1,000 or so things. So you're telling me that maybe it spans 2 pages, but probably my little array is on 1. So I just kept getting the same entry over and over and over again. And here's the problem. The reason why I was walking back and forth like a crazy person is because I was trying to illustrate that when the MMU has to go to RAM, it's slow. Because RAM is not on the CPU. RAM is a separate entity. The MMU is on the CPU. RAM is somewhere else. It is connected to the CPU via the address bus. When you leave the CPU, it actually takes time to travel, have signal travel along the wire. That's not free. And then once you arrive at the RAM, you have to ask the RAM to give you something, and then you have to send that signal back, and it actually takes time to arrive. And a funny story about this, it taking time for a signal to propagate down a wire. So the old Cray supercomputers, Cray is one of the big, if you don't know much about supercomputers, look up the Crays. The Cray 1 serial number 1, it's at the Mountain View Computer History Museum, and the tradition is to give it a hug. So if you're there, go give it a hug. It's this giant artistic looking piece, it's awesome. What they used to do is, because it was a vector system, and because they were aware that the signals could, depending on the length of the wire, it would actually take a different amount of time for the signal to propagate along it, they actually made the wires different lengths to ensure that it all arrived at the same time. It's funny little quirks. Anyways, it takes time for signals to propagate along a wire. So going to RAM all the time is really slow. Wouldn't it be nice if we cached that page table entry locally, like on the MMU, instead of always having to go to RAM each time? Well, that's exactly what an MMU actually does. An MMU has something called a TLB, Translation Look Aside Buffer. It is a cache for page table entries. And that is exactly what we're going to do. Is we are now, when we try to do an address translation, we first ask the TLB, hey TLB, do you have this? And if the TLB has it, then we just use our own local cache to do the translation instead of actually having to go to RAM. And if the TLB doesn't have it, i.e. a cache miss, then, and only then, we actually go to RAM to get it. And yes, that will speed us up. So, as it turns out, there are two ways that you can implement the TLB. The first way is called a hardware managed TLB. Yeah?
Let's say I have two threads running some code and they both, like there's some critical section. If I have my local copy of stuff and I modify it, does marking it volatile make me not use the TLB? So that it's stored in one place, or do we still use the TLB as our local copy things?
So the TLB doesn't cache the address translations, it caches the page to frame mapping.
Okay.
So not how each individual address translates, it's caching the actual page to frame mapping.
Okay.
So that you actually get the benefit of like a whole page of translations. Otherwise, we'd have some problems. In which case, volatile would have to be used to deal with that.
Okay.
Volatile is separate.
Yep.
TLB is separate. All right. So the first way that we can implement our TLB is a hardware-managed TLB. And what happens with a hardware-managed TLB is when we get an address on the MMU and we want to translate it, first, as I said, we're going to check the TLB to see if it is there. If it is there, we get our frame number. We perform our address translation as normal, we go about our business. If, however, the TLB, there's no entry that is in the TLB miss, then what the hardware is going to do is the hardware goes to RAM, gets the page table entry, tries to put it into the TLB. If it can't fit because the TLB is full, because caches are small, then the hardware will choose an entry to kick out, insert the new entry, return the frame number, and now the translation can actually go on as expected, and the TLB has been updated. That is a hardware-managed TLB. Advantage, it's fast. If you can do it in hardware, do it in hardware. Downside, in order for us to use a hardware-managed TLB, the hardware must dictate to the programmer what their page table entries look like. because the hardware needs to know how, when it gets a TLB miss, how to interpret that page table entry and update the TLB. Which means that I'm telling the programmer what to do. Programmers, I don't know about you, but I don't like being told what to do. I want flexibility. Or I'll try to shove it down your throat in ways that are unnatural. So the upside is speed, the downside is there's no flexibility. We are enforcing a hardware restriction onto the user, and the kernel must obey it. So the other option is to use a software managed TLB. And this is what most people actually do, and OS 162 included, it uses a software managed TLB. What a software managed TLB does is it's the same if there's a TLB hit. But if there's a TLB miss, that's where things differ. On a TLB miss, the MMU throws an exception. It says, I don't know, you figure it out. The kernel responds. And you might have seen this, TLB miss on load, TLB miss on slightly different issue, but when the kernel receives that TLB miss, it says, oh, this must not be in the TLB. And so the kernel will do the lookup into the page table, extract the page table entries, which are stored in however the kernel decided it wanted to do it, and then the kernel is responsible for finding a free slot in the TLB, adding the new entry, evicting somebody if it needs to, and then after it has updated the TLB, we return, and the instruction that caused the exception will be re-executed, and except this time it will succeed because the kernel updated the TLB. This gives us also flexibility in which cache eviction strategies we are using for our TLB. And just a word of warning, right now, OS 161 has no cache eviction strategy. If the TLB in OS 161 is full, OS 161 panics and dies. Yep, guess what? You get to fix it. It's like 2 lines of code. Now, because we have changed our hardware, we also must change what happens on a context switch. Do you have a question?
How's the number of key provided in the kernel?
How's the which?
The number of key.
The number of key. What's key?
The address of the kernel. The
Oh.
kernel needs to know about key in order to treat it.
Okay, so the address key. So as part of the MMU throwing that exception, it will put the virtual address in probably one of the parameter slots of the trap frame. Just like we do with system calls, we can put it in a specific register in the trap frame to let the kernel know what the fault address is. All right, so now what we have is a problem with what do we do with our TLB on a context switch. So we know that we update the MMU on a context switch by changing the value in the page table base register to match that of the new process that is running. But we must also now change the TLB because all of the page to frame mappings that are cached within it are with respect to the running process, which means that when I have a context switch to threads of a different process, then I must also clear the TLB out so that I don't have any of the other processes mappings in there and I don't do bad things. Now, some of you, how many of you have seen a function while you've been implementing A2A called ASActivate? You haven't seen that one? A few people? It's probably been really, really tempting for you to call it because you're like, wow, I created an address space, I should activate it, right? Okay, don't call that function, please. It does not do what it advertises. ASActivate is probably the single worst named function in that entire operating system. It doesn't activate shit. Yeah, do you know what it does? It clears the TLB. As I said, it's a very bad named function. You do not need ASActivate on A2B or A2A, but you do need it on A2B. So if you are calling ASActivate, it's not going to hurt anything, technically speaking, but it's completely pointless. I like to give people a forewarning about that because I see a lot of it in offsets. Yep.
That means you remove power and you remove all calls to the factor, the last run.
Sorry, I can't hear this gentleman here.
If you remove all calls to the factor, what would happen to your
If we removed all calls to AS activate, we'd have a problem. Because if I then ran multiple processes, my TLB would never be cleared, which means that I would be translating addresses for process B, possibly using process A's translations, which means I just broke process isolation. That's really bad. You gotta clear that TLB out. All right. So here is a picture of a TLB entry for the MIPS R3000, which is the chip that we are using. It is a 64-bit entry, and our TLB can actually fit 64 of these within it. It's not too bad. The high order word contains the page number in the upper 20 bits, and the low word in the upper 20 bits contains the frame number. The low word also contains a bunch of bits for valid write permissions, and so on and so forth. Now you might be wondering, what is this 6-bit PID field that we have here? Does that mean the PID of whose entry this belongs to? Theoretically speaking, that is exactly what that could be used for, except it's not used. And in fact, this is something that exists in pretty much every TLB entry in even Intel and AMD chips, and up until very, very recently was not. It is now. What this does, this magical field does, is one of the downsides of having a context switch is that you're clearing out the TLB every time. Which means that when a process comes back to running again, all of the things that it cached before are gone and it has to start again. We have no cache affinity. That field there can be used for, amongst other things, cache affinity. It can be used such that when we come back to running that process again, we don't just check for the page number, we now map page number and PID. So we don't have to clear the TLB on a context switch. That field can also be used for security reasons. The process can actually keep track of which process ID is actually running right now, and will only perform address translations actually if the two PIDs match up. So that's adding isolation as well. And that's a fairly new thing that we've come to use.
So the MIPS just like preemptively save those 6 bits there just in case?
Yeah, so those bits have actually been in most TLB entries for many, many architectures for like decades. It's just that no one's ever actually really used them. And I don't know all of the details quite, but I think with the Spectre and Meltdown thing, this started to be like a real thing. Hey, we have to use this. So I believe now Linux uses it, and Intel uses it. Again, I don't know all, but I know it is something we are using now. But yeah, no, MIPS had this idea years ago. Everybody's had the idea. It's just, did you use it? All right. So with that, that's actually the end of paging and the end of the discussions of our theoretical different implementations of virtual memory. The advantages, of course, of paging are that we now have no fragmentation in our, or no external fragmentation of physical memory. We do get a bit of internal fragmentation, but here's the thing. If your page size is 4 kilobytes, that's so tiny. Maybe at best you waste 3 kilobytes of one of those pages. If you look at most modern systems which have tens of gigabytes of RAM, we don't care, even if we had 1,000 processes running, about each of them wasting 3 kilobytes. That doesn't add up to much. So even though there is a little bit of internal wasted space with this method, it's insignificant. And we have no external fragmentation now, so we're happy. That's great. We were able to shrink the page table size by using multi-level paging, and to improve the performance, we added, of course, the TLB. All right. So, If you're curious about the history of this actually goes back to the early 60s, late 50s. There was the first paper in paging. This isn't a new idea. Now, if we were looking at modern operating systems, the ones that you have sitting in front of you, so DOS, predecessor of Windows, didn't use virtual memory. The earliest versions of Windows didn't use it. And when they did start using virtual memory, they actually started with segmentation. They didn't move over to a full paging model, I believe, until after Windows 3.1. So it was actually very, very recently that they moved on. Linux, of course, does paging, and Linux supports a 4-level page table with 48-bit virtual addresses, and very recent kernels are also supporting 5-level paging with 57-bit addresses. And I'd really like to know why they decided to use 57, because it's odd and it's obviously not a power of 2. It seems very bizarre. I haven't looked into it in a while. All right. So now, what I'd like to do is move our focus away from more theoretical implementations of virtual memory and start to talk about how OS 161 implements its virtual memory. You've heard me actually talk about its implementation before. It's called DumbVM, and it's called DumbVM because it is dumb. Really, really dumb. So technically speaking, we are using 32-bit physical addresses and 32-bit virtual addresses with our MIPS system. Our MIPS R3000 MMU is a paged MMU with a TLB that supports 64 entries. Very respectable if you consider R3000 is actually pretty old. But OS 161 does segmentation. Now you might be wondering, how did we shove segmentation down the throat of a paging MMU? Well, this is how we did it in OS 161. OS 161 takes each segment and sets it to be a contiguous block of pages, and it requires that those pages map to a contiguous block of frames in physical memory. So if we need 12 pages for the code segment, then I need 12 contiguous frames for the code segment in physical memory. So it is segmentation in the operating system, but it is paging in the MMU. And by the way, if you're curious, in assignment 3, you're going to fix it. You're going to add paging back. You're going to combine paging and segmentation together, which is actually an excellent way of doing virtual memory. Well, it's a very reasonable thing anyways. The implementation of the virtual memory for OS 161, you'll find in a file called dumbvm.c. And anytime our MMU throws an exception, the function that is going to handle that exception is called vmfault. And you may have encountered this. If you've seen a TLB miss on load or a TLB miss on store, that is the MMU telling you that you are trying to read or write to an address that is not valid. In which case, vmfault is opened up and it will handle it appropriately from there. So, this is the structure of an address space then. Yep.
So if it's continuous blocks, then we wouldn't be able to
No, because we are going to, so we in the operating system are setting it up to be allocated as if it's segments, but we will treat the MMU as if it's pages. So it's just how we have mapped the pages into physical memory is as if it's segments. And when we're trying to compute the fault address, when we're trying to figure out which page it's on, we'll use segment math, convert it to the page, update the TLB, and the MMU will go back to paging happily. It's very weird. You'll see. All right, so if we look at the address space structure for OS 161, we will note that there are 3 segments to the address spaces for OS 161. We have a code segment, a data segment, and a stack segment. In the address space structure, because we are using segmentation, we keep track of the start physical address, the number of pages, i.e. the limit in pages of each of those segments, and the start virtual address of that segment. We are not going to set aside and create a segment table. We are also not doing this by setting aside higher order bits for the segment number. You'll see in a minute why we don't do that. So for the code segment, we have vbase is the virtual base address, which is the first address you can see in the diagram of the virtual segment region. And then that is our code. And then we have pbase, which is the beginning of the code segment in physical memory. Those are going to be paged aligned because, again, the MMU uses page. Then we have the data segment, which is vbase and pbase 2. So again, we have the virtual base address, the physical base address. And for both of those, we also keep track of the number of pages each of those segments actually occupies. You will note, however, for the stack segment, we don't have all of those things stored. And in fact, the only thing we store for the stack segment is its physical base address. We do not store its virtual base address, and we don't store its size. And the reason for that is because OS161 stacks for the user program are of a fixed size and at a fixed location. In OS161, your stack is 12 pages or 48 kilobytes. And there is no discussion. It is a macro in the OS. Please don't change it. And it always lives at a very specific address. And since it is true for every single process, there is absolutely no reason for us to store that information in the structure because it doesn't change. All right. So, how does OS161 do its own address translation? So let's keep the MMU out of this for now. Well, what we're going to do is, let's suppose we get a fault address. And now I need to figure out which segment that fault address is in. Is it in the code segment? Is it in the data segment? Or is it in the stack segment? And once I figure out which segment is in, how do I translate it to its physical counterpart so that I can go about and update the MMU appropriately? Well, this code here I have stolen directly from dumbvm.c, and what it does is it figures out which segment it is in, and then it actually translates that virtual address into the physical address. So the first thing that we do is, for each of the segments, we compute the base and the top. The base is the low address, and the top is the high address. So for the code in the data segments, that's literally just grabbing the information out of the address space structure. Base is provided directly. Top is base plus number of pages times page size. That's the top. Yep.
So is top the first non-valid address?
Yes.
Okay.
Yeah. So zero-based, it's it's traditional. All right. However, for the stack, we actually have to calculate this. So what we actually find is the stack, and I've got to make sure I get my math right here because I always mess up my math. So our stack, if you look at OS161, so if this is our virtual memory, our stack, the last addressable byte in my stack lives at this address here. So technically, the top of the stack is this address here. And I already know that. Stack top is this address right here. So I don't have the base address, however. So in order to calculate the base address, from the user stack's top, I subtract the number of pages we set aside for the stack multiplied by the page size. Which is going to mean, a number you might want to memorize, that the stack base, and just let me make sure I got the number right, 4. That's stack base. Once I know the base and top of each of the segments, I can then take my fault address, and instead of, extracting bits or any fancy things like that, no, we're just going to do a comparison. We're going to check, is this for fault address greater than or equal to the base but less than the top? And if it is, then it's in the code segment. And if it's not in the code segment, we compare it to the data segment. And if it is, then it's a data segment. Otherwise, we compare it to the stack segment, and if it's not in the stack segment, we return an error saying this is an invalid address. Which causes panic and death, of course. Because everything in OS 161 right now is panic and bad. Alright. Now, how do we actually do the address translation? So let's suppose we have an address and it is in the data segment. Then what we're going to do is we need to calculate the offset within that segment. So we take fault address and we subtract the base of that segment from it, which will give us our position within the segment. And then we are going to add that offset we calculate to the physical base address. We're done. That's it. And then if I wanted to actually update my TLB now, I take the upper 20 bits. There's my page number. And the upper 20 bits of the physical address, there's my frame number. I can now update the MMU. It now has the TLB enter in it. So that's how we put the two together. All right. Now, the next slide would have us actually start doing some translations, but there's like 2 minutes left of class. It's Thursday, so let's pretend it's Friday, and we'll work on A2A.
Every time I see you, I could die.
Stop. Stop.